Hi, this is lecture 26 of M2 In last session, we have seen the notion of what is called integrable function. A bounded function f from a to a comma b to r is said to be integrable if some condition is satisfied. What is it? For this f, we have assigned two real numbers, one is u of f, one is L of f. This we have called as upper Darboux sum, this we have called as lower Darboux sum. Then we have said if these two are same, uf is equal to Lf, then we said f is integrable on AB and this value they are same, so I can take any value and that value is what we are calling as integral of f on AB, that we are denoting by this symbol. Then there is another description of integrability. This is what we are calling as Darboux integrability condition. A function f is said to be Darboux integrable if this condition is satisfied. To do this, we need the notion of what is called partition. I do not repeat that again, but partition is the starting point. Using a partition, we introduced UPF, then we took supremum infimum, something like that, then we got UF. Similarly, LF, if they are same, then we say f is Darboux integrable, and this value we are calling as integral of f on AB and we are denoting by this symbol. Now, there is another way to introduce integrability. A function f from a comma b to r, not necessarily bounded. When we are talking about Riemann integrable, not necessarily bounded. For this, we assigned something called Riemann sum. Given a partition P and a sampling T bar for this function f, we assigned a real number. We have done this for each partition P and each sampling of the partition. What is partition? Just find set of elements. This sampling is you are making a choice of element from each subinterval of the partition. Now, what is that Riemann integrability condition says? A function f from a comma b to r is said to be Riemann integrable if given epsilon positive there is a partition P of AB. I forgot to say something before saying any of this. Just like in the case of limit of a function, we need to specify a real number. A belongs to R. A function f from a comma b to R is said to be Riemann integrable if there is an element a belongs to R such that some condition is satisfied. What is it? For epsilon positive, there is a partition such that for every refinement of the partition P, refinement Q of the partition P, and for any sampling T bar, what we have is this Riemann sum for the partition Q is related to A in this sense. Then I said without proof that these two conditions are equivalent. Riemann integrability condition is equivalent to Darboux integrability condition. So, whenever we say integrable, one can use any of these two ideas depending on the situation. Then I have said that just like in case of continuous functions or differential functions, one need to check algebra of functions. When two functions continuous, sum is continuous, product is continuous, difference is continuous. When a function f that is nowhere vanishing, 1 by f is continuous or 1 by f is differentiable, like that we have seen. Then I said checking for integrability of f plus g and f minus g is slightly easier than others. To do others, we need an extra result that we can use, and what was that result? A function f, a bounded function, said to be Riemann integrable, Darboux integrable, whatever it is, because I said they are same. So, if some condition is satisfied, what is it? For every epsilon positive, there is a partition P such that UPF minus LPF is less than epsilon. That is what it means. This is partition, this is epsilon positive. This we have called as Riemann condition. So, one can use this to prove that some function is Riemann integrable. One unfortunate thing here is the following. This strategy allows you to verify if a function is Riemann integrable or not, but it does not really say what is the integral of f. See, you do not see anywhere here at least. See, maybe if you are slightly lucky, then in this process you might get the what is the element also, but it is not very clear why one should achieve that that integration also. Yeah. So, in any case, suppose we are checking only for integrability, then this is definitely useful. So, let us do one example where we use this construction, where we use this condition to check if some function is integrable. So, I said about f plus g and f minus g, that I did not really prove, that was an exercise. Try to convince yourself that that is true. You can use any of these two conditions. I mentioned two conditions. You can use any of these two, or you can use this also, it does not really matter. This is an equivalent condition. If this is true, then it is Riemann integrable. If it is integrable, then it is then this condition is satisfied. I have proved this also, so you can use this. Now let us try to check that product of two integrable functions f g a comma b to r is integrable. If f and g are integrable, then the product is integrable. So the question is, how do we proceed? So unlike the case of see, look at this condition. Suppose we want to check this in this way. First of all, we need to look for some a belongs to r, then proceed further. So in case of sequences we have done the same thing, right? We just thought of one real number which looks like the limit of the sequence, then we did some combination, something like that, then we sometimes we succeeded, sometimes we did not succeed. So in any case, that time it was easy to guess such a real number, but here if I give this function, it is not very clear what is the element that I should guess. But as I said, check looking for integrability, looking for confirmation of integrability, one can use this idea. All you need to do is the following. Suppose I give you epsilon positive, you should get a partition P such that this condition is satisfied, that is all. Now before doing any such kind of thing, let us at least write down what does it mean to say that f is Riemann integrable, f is integrable, that means this is satisfied. So for f there is a partition, let me write down, let me fix epsilon positive first. There is a partition P epsilon of AB such that what do we have, u P epsilon f minus L P epsilon f is less than epsilon. G is also Riemann integrable, is also integrable. So there exists a other partition P let me write down this as f just to make sure there is no confusion. This I am writing as P f, let me write the other thing as P epsilon g, that is the only difference. And then the same thing, that the condition is same, P epsilon g minus L P epsilon g comma g is less than epsilon. Now we have two conditions. Now the problem is these two partitions may not be same, may not be related at all. So how do I see this is where the notion of refinement comes to rescue us. Given two partition, one can consider their union. If I am seeing them as just a subset P epsilon g, this is a partition, these two are finite subsets of AB, their union will be a finite subset of AB, and this is what we are calling as a common refinement. I mean any refinement of this thing is also called common refinement, but this is special, at least this is special in the sense that we will see now. What do we have is we have a partition, this I am calling as P epsilon, this I am calling as P epsilon. We have a partition. Now let us see what happens to F and G in this. So we are taking a we are trying to see whether U of P epsilon F minus L of P epsilon F is still less than epsilon or it is not. Similarly, let us you can check for G also. So let us do for F first, then see if it does not have any special property then compared to G. So once I know for this, then the same thing should work for G also. So let us check this. Now we are trying to see whether this is true or not. As P epsilon F is contained in P epsilon, so P epsilon is a refinement of P epsilon F. There is a relation between U P epsilon F and U P epsilon F of F. What is the relation? The relation is U P epsilon F less than or equal to U P epsilon F of F. Now what about L? L P epsilon F is greater than or equal to L P epsilon F of F. This implies what? Minus L P epsilon F less than or equal to minus L P epsilon F comma F. So now what do we have is this element is less than or equal to this, minus of that is less than or equal to this. So when you add these two, it will be less than or equal to this plus this. So U P epsilon F minus L P epsilon F is less than or equal to U P epsilon F F minus L P epsilon F F. This we know to be less than epsilon. So what do we have for this partition, that is refinement of PFF, PEF and PEG common refinement? What we have is this difference is less than epsilon. So as I said, if it is not special here, one can do the same thing by applying by replacing F by G. So now what we have is F and G are integrable. So there is a common partition P epsilon for both F and G in the following sense. Given epsilon positive, one can find a P epsilon such that U of P epsilon F minus L of P epsilon F less than epsilon this is, and U of P epsilon G minus L P epsilon G is less than epsilon. Now we are trying to see whether one can do the same, one can get this inequality. Right? Suppose we instead of F and G separately, suppose we take the product F G, do we still get the same? That is sufficient, right? Suppose we get this P epsilon F G minus L P epsilon F G, suppose this is less than epsilon, then we are done. We need not get, it is not necessary that we need to do this for only this P epsilon. If there is some partition depending on epsilon with this condition, then we are done. This says F G is integrable. How do you know that? Riemann condition that we mentioned before. Okay, so we are trying to see whether this is true or not. Okay, so what is this? Let us focus on this part, U P epsilon of F G. This is equal to summation F G restricted to xi plus 1, then we are taking supremum of this times length of this interval. What is this? Xi plus 1 minus xi, that is this portion. We have this also, let us write down that also, minus summation infimum F G restricted to xi plus 1 times xi plus 1 minus xi. We are trying to show that this component is less than epsilon. We may succeed, may not succeed, the different thing, but see, observe the following. In these two, one thing is common, that this part is common. So this is something as summation supremum fg restricted to some interval minus infimum fg restricted to some interval times xi plus 1 minus xi. So it makes sense to focus on this first, then we might add this and then see what happens. This I is from 0 to n minus 1. So let us focus on this. For this, what the following trick you will see many times. The trick is the following. We'll fix some index I, 0 less than equal to I less than equal to n minus 1. Take two elements x comma y in xi plus 1, and then look at the difference fg of x minus fg of y. That is what it is, right? Supremum of fg restricted to something minus infimum of fg restricted to the same interval. So for that we took two elements in this, and then we are trying to see what happens. This is equal to f of x g of x minus f of y times g of y. The problem is the condition of that we know about g is just this. So if you are trying to relate this with this, what we have is g of x minus g of y are for two elements in x comma y in this interval. This condition gives some idea about gx minus gy, but here we do not have that choice. So we use the same trick that we have done before. We add and subtract some portion so that we get what we need. So let us do that. Fx gx minus fx gy plus fx gy minus fy gy. I think the idea is clear why I am doing this. If I take fx common, I get gx minus gy. So it looks like I'll be able to use this idea, this observation. So that is the reason why I am doing this. Similarly this also. So this is same thing as fx times gx minus gy plus fy gy times fx minus fy. Now what? There are two elements in the interval xi plus 1. What can we say about this difference? Observe the following. X belongs to xi plus 1. So gx is less than or equal to supremum of g restricted to xi plus 1. This much is clear at least. Similarly, y belongs to xi plus 1. So infimum of g restricted to xi plus 1 is less than or equal to g of y. I am just writing the definition of what is supremum, what is infimum. Now let us keep this as it is. Let us change this by putting a minus sign on both sides. What do we have? See, because we are dealing with gy, minus of gy, not just gy. So we want a minus here. If I put minus here, I have to put minus here also, and then I have to change this sign also. So now what do we have? Minus gy is less than or equal to minus infimum of g restricted to xi plus 1. Here I have minus gy. So I want something to do with minus gy, but here there is only plus gy. So if I put minus, this will feel bad, I should put minus here. If I put both sides minus, then this also should be changed. Now just add these two inequalities. What do we get? Gx minus gy is less than or equal to supremum of g restricted to xi plus 1 minus infimum of g restricted to xi plus 1. Now what? So we have some now we got some approximation for this part, same thing for this also. All I need to do is I need to change g and put f. Now fx is less than or equal to supremum of f, right, there is nothing surprising. So fx is less than or equal to supremum of f restricted to again xi plus 1 or maybe on the whole f, it does not really matter. Similarly gy is less than or equal to supremum of g. Now one naive step that we can do is the following, just write down that this thing is less than or equal to maximum of this times whatever we got for this inequality, what is this supremum minus infimum plus gy less than or equal to maximum of g, and this replace it with this, replace with f. But that is not really a good idea, because a less than or equal to b and c less than or equal to d does not imply ac is less than or equal to bd. This much you know at least, right? One of them has to be positive, something has to be positive, but it is not very clear whether everything is positive here. Fx is positive, I do not know. What about this, I do not know. This it is not very clear whether it is positive or not. So just to be on the safe side, let us change the starting point. Let us maybe we can change it here also. What I will do is I'll write down this less than or equal to, I will put mod everywhere, then maybe then you will be able to use it. So this whole thing is less than or equal to modulus of f of x times modulus of gx minus gy plus modulus of gy times mod fx minus fy. Now this thing is less than or equal to, see f is defined from closed interval a comma b to r, so it attains maximum. So one can just replace this less than or equal to m times mod f. Now what about this gx minus gy, I know is less than or equal to this, but suppose gx minus gy is negative, if I take modulus then I will get here gy minus gx, right. So then I should get a minus sign, is it so? No, observe the following, this thing is true for every x comma y. Even if I put y here, x here, or x here, y here, it does not change this inequality. It may take some time, but that is the truth, and yeah, just spend some time, you will be able to realize what is happening here. This thing does not depend on what x and y are. If I put y here, x here, that is still true. So irrespective of whether I take modulus or not, this thing is still less than or equal to this minus this, and this is always greater than or equal to this. So I do not have to put modulus here again, this is already positive. So this is less than or equal to supremum of g restricted to xi plus 1 minus infimum of g restricted to xi plus 1. Let me write down that plus 1. This is one part. Then one can do the same thing for m times mod g and write the same thing, replacing f with replacing g with f. Now what we will do is the following, this is true for every x comma y, where is the starting point, this is true for every x comma y inside this interval. So what does this say, if I vary x over all this is still true. This element is less than or equal to this element minus this element, less than or equal to some fixed quantity here, whatever I have written here, this here. So, once we vary x, we have to replace fg with the supremum of fg restricted to xi plus 1. That minus we are replacing with minus fj of y, infimum of fg restricted to xi plus 1. This difference is less than or equal to m times mod f times something plus m times mod g times something. This something is exactly what you will see in this inequality. Where is it? This. If I focus this one of the subinterval xi plus 1, what we get is just this supremum g minus infimum. So, now suppose you add up all those indices, then what you get is now you need to multiply this whole thing by xi plus 1. Similarly, here also this concludes that u p epsilon fg minus L p epsilon fg is less than or equal to, see this thing when I put xi minus 1 and this also xi minus 1, this thing is less than or equal to epsilon. So, this is mf times epsilon is less than, so this is gone, plus m times mod g times epsilon. So, you can take epsilon common, that is equal to epsilon times m times mod f plus m times mod g. So given epsilon positive, we got a partition p epsilon such that this difference is less than epsilon times some fixed constant. We know this is as good as getting a partition such that this difference is less than epsilon. This is not there. Those two are equivalent conditions. What does it say? It says fg is integrable. Fg a comma b to r is integrable function. Yeah, so this is about algebra of integrable functions. One of the properties, if f and g are integral functions, their product is integral function. It took some time. It's a long proof, but when understanding this proof, this will make the idea of integral functions clearer. See, the reason why writing down proofs is important is it will make your understanding better of the basic concept. So that is the main idea why I am writing down this proof, and it is too lengthy. So this is same thing with f plus g, f minus g, and 1 by f. For 1 by f there is other condition that I will add in the lecture notes. But the idea is, if you write down this kind of thing, it will make your understanding of integrability clearer. That is the main purpose. So now, after this very strong result, let us do one simple example. Let us check that some function is integrable. We did not check that now, because one reason that I am not doing many examples for integrable functions is the following, that you already know how to compute integration, maybe much faster than what I can do. So teaching you how to compute integration or doing some examples may not be a good idea. So what I can do is I can try to explain what is happening there. For example, this is what is happening, that if I take two functions that are integrable, the product is integrable. But let us do one example, at least let us do one example. The basic example that I can think of is a identity function f from a comma b to r is it integrable, x goes to x. I am sure you know that it is integrable, and you also know that integral a to b x, should I write something here, is equal to x square by 2 a to b. So this is equal to b square minus a square by 2. Some of you might already know this, but this does not, we are saying that if f is integrable, then we will denote integration of f by this symbol, but it is not very clear how these are related to this, to whatever we are doing. So let us see. Firstly we will see that it is integrable, then we will see that integration of this is this let us prove that it is true, prove that this is actually true, not just the formula. Now what is the first step to proceed here? Firstly, let us check that it is integrable. As I said, checking integrability is slightly easier than finding the integration, finding the integral. So there are two parts. One is check that it is integrable, find the integral. See, there are two different things. Just like in case of convergent sequences, checking for that the sequence is convergent is easy because one can just check that it is Cauchy sequence when you are dealing with R. But even if you know that sequence is convergent, when you are trying to use Cauchiness, it does not say what is the limit, it only says there is some limit. So here the same thing, the Riemann condition, whatever I mentioned before, it does not say what is the integral, it only says there is integral exist, that is all it says. So let us do one step at a time. Let us first check that this function f is integrable. What do we need to do for that? Given epsilon positive, we need to look for a partition p epsilon such that u of p epsilon f minus L of p epsilon f is less than epsilon. This is what we are trying to see. Now let us do it a very basic step. Fix AB, forget about epsilon positive and p epsilon. Let us first check what do we know about this UPF and LPF for a simple partition. A partition that I am considering is the following: just 3 elements. If it is only 2 elements, there is nothing, we cannot really do anything. A common partition, it is a finite set containing A and B. So let us put one more element just to make it interesting, not difficult, interesting. A is equal to x0, let me put x1 and x2, this is B. This is one partition. Let us check what can we say about UPF minus LPF. So what is UPF? As I said, this is equal to U upper sum is related to supremum. Supremum of f restricted to x0 x1 interval, x0 x1 times the distance of this interval x1 minus x0. Now what about the other part? Plus supremum of f restricted to x1 x2 times x2 minus x1. Now because f is a identity function, so the supremum of f restricted to that, it is just the maximum, the end element of this interval. Here it is x1, infimum will be x0, similarly here supremum will be x2, infimum will be x1. So let us just write down that is equal to x1 times x1 minus x0 plus x2 times x2 minus x1. Let us finish this computation. What is this? x1 square minus x1 x0 plus x2 square minus x2 x1. Now let us check what is the LPF. LPF is equal to infimum of f restricted to x0 x1 times x1 minus x0 plus infimum of f restricted to x1 x2 times x2 minus x1. As I said, this is same thing as x0, this is same thing as x1. So let us write that down. That is equal to x0 times x1 minus x0 plus x1 times x2 minus x1. What is this? This is x0 x1 minus x0 square plus x1 x2 minus x1 square. Now what we are trying to see, what? We are trying to see the difference UPF minus LPF, what is it? That is what we are trying to see. So UPF minus LPF is what? So let us compare this. X1 square, do we have x1 square here? Yes. If I put minus here, there is a plus here. So these two does not get cancelled. So there is a 2x1 square. Let us write that down. It is 2x1 square. Now what is the second thing? x1 x0 is there. there is x1 x0, but if I put minus here, we are doing UPF minus LPF. So there are 2 x1 x0 with a minus sign. So this is minus 2 x1 x0. Third element is x2 square, and there is no x2 square. So this is just 1 x2 square. x2 square. Now what about x1 x2? There is x1 x2 here. There is x1 x2 here. If I put minus, there will be 2. So I should write down that minus 2 x1 x2. Now what about this part? This we have already used. x0 square we did not write down that. So let us write down that is x0 square, just 1. If I put minus here, minus minus is plus. So that is just 1 x0 square. x1 x2 we have already mentioned it here. x1 square we have already mentioned it here. So UPF minus LPF is this. So what we have is x0 square plus x2 square, 2x1 square minus 2x1 x0 minus 2x1 x2. Now observe some nice thing that is happening here. So one can split this into the following thing: x0 square plus x1 square minus 2x0 x1 plus x1 square plus x2 square minus 2x1 x2. I am just writing 1, 2, 3, 4, 5, 6 terms. 1, 2, 3, 4, 5. So this I am writing as x1 square, and that is all. So x1 square, this is something as x0 minus x1 whole square. This is x1 minus x2 whole square. So this is equal to x0 minus x1 whole square plus x1 minus x2 whole square. So now what we have, UPF minus LPF is maybe not necessary to write down. I will just copy paste this. It is just this. Now there is some pattern here. Suppose you take a partition with n elements, what we get is the following. You get summation I is equal to 0 to n minus 1 xi minus xi plus 1 whole square. This is what you would get. Right, for n equal to 2, what we have is x0 minus x1 whole square plus x1 minus x2 whole square. N equal to 2 means it should stop at 1 only. So this I am leaving as an exercise. It is not very serious also. Now what we have, we want to show that this difference is less than epsilon, not this, but given epsilon positive, one can find a p such that this thing is less than epsilon. That is the strategy. So given epsilon positive, we need to find a partition p epsilon such that UP epsilon f minus LP epsilon f is less than epsilon. See, one nice thing would be the following, that this is what is this? This is length of the interval x1 x1 plus 1. Suppose I did not mention in the last session, there is a nice, given any subset of any closed interval of R, there is a one nice partition that we can think of, the following. So 0 comma 1, suppose we take this this thing, you fix any n, fix n is equal to 3. Now one can partition this into 3 parts of equal length, 1 by 3, 1 by 3, 1 by 3, 2 by 3, 1. This difference is 1 by 3, this length is 1 by 3, this length is 1 by 3. So there is nothing special about n is equal to 3 or this 0 comma 1. You take any n and any interval. So let us take AB, A comma B. Then I want to split it into n parts. What is that I need to do? A minus B, B minus A, this is B less than A. I am trying to split this into n equal parts. So I should start at A and look at this much length and put a point there. So this is one way to partition of equal length. What is the use here? In that case, so this thing I can take as a common point. So what we have is, now fix epsilon positive, we don't really know what n we should fix. I mean n is number of elements in the partition, but let us fix some n, and let us after doing one or two steps, let us come back and fix what n we want to do. So we have let me copy paste this first. So this thing, suppose these are the partition is of same length, then this is equal to summation I is equal to 0 to n minus 1. Suppose this is of length b minus a by n, then what do we have? This thing is equal to b minus a whole square by n square, right? What I want is and how many times I have this? I have 0 to n minus 1 is n times, so I can just take this as common, b minus a whole square by n square times n. This is equal to b minus a whole square by n. What I want is, I want this to be less than epsilon. Can I do that? Given epsilon positive, can I find a n belongs to n such that this is less than epsilon? Do we know that? Yes, we are doing this from a long time. Argument property, 1 by n is given epsilon positive, one can choose n belongs to n such that 1 by n is less than epsilon. Now you can reduce further and then say you can actually find n belongs to n such that b minus a whole square by n is less than epsilon. So this is possible, and then we do once I know what n I should choose, now split this interval AB into n parts of this length b minus a by n. So once you know what n is, split this AB into n parts of this length b minus a by n, and then you know what I have done here. This is equal to b minus a whole square by n. See, this is what b minus a by n. So this whole square means what, b minus a square by n square. Because there are n elements here, this comes out, and I need to add it n times. That is same thing as b minus a square whole square by n. And I want this to be less than epsilon, and I can always do this. Given epsilon positive, there is a n belongs to n such that b minus a whole square by n is less than epsilon. So what does this say? This says this f is integrable. So this implies what? The identity function f a comma b to r is integrable. Now checking for integrability is one thing, and proving computing the integral is a different thing. So this I will add in the lecture notes, I will not do it here, it is already getting extended. Now what we have seen is, we know what is the integrable function, then we have seen product of two integrable function is integrable, we spent so much time, and then we have seen that identity function is integrable. Then observe the following, see then in the beginning of the course we have done about some special. In the beginning of the course we have spent some time on some functions, some special kind of functions. What are those? Continuous functions, monotone functions, continuous functions, and all that. So one obvious question is, how much, see in this session or previous session I did not mention anywhere that the function is a continuous function or monotone function or bounded function I mentioned, that is the starting point. So I did not mention about anything about the other two functions or three functions. Bounded I mentioned. What about a continuous function? I did not mention anything. Monotone function I did not mention anything, and uniform continuous functions I did not mention anything. So one obvious question is following, suppose I am starting the continuous function on the bounded interval, do I know if this is integrable or not? Suppose I take a monotone function, is it integrable or not? Suppose I take uniform continuous function, is it integrable or not? See, these are small questions that you need to ask yourself. Let us start with this. So let us take a function f a comma b to r. I am already assuming it is bounded, continuous. One thing to observe the following, whenever you know that a function is continuous on a closed interval, closed bounded interval a b, you know that it is uniform continuous. What is the benefit of that? One can write in the following: given epsilon positive, there is a delta positive such that whenever x minus y is less than delta, we have fx minus fy is less than epsilon. See, this thing should remind you about partition into some length related to delta, and this thing should remind you about supremum of f minus infimum of f, that kind of thing. These I have already mentioned before, but even before I proceed to the proof, you should realize what you should guess at least what I am going to do. Okay. Now what? After fixing epsilon positive, let us take some partition P. P epsilon is equal to x0, that is equal to a, x1 dot 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 xn, that is equal to b. I am not fixing anything about this number here, but I know that if I involve delta, it will make my life easier here. So let us first check what is UPF minus LP epsilon f. Or before that, let us at least focus on this portion: supremum of f restricted to xi plus 1 minus infimum of f restricted to xi plus 1. Again, for this what we need is the following, that the same trick that we have used before. You take random points x comma y belongs to xi and xi plus 1, and we are trying to see what happens to fx minus fy. Okay, so now there is a small problem. Suppose I know that this x and y are of distance less than delta, then I know for sure that this difference is less than epsilon. But here I am taking two elements from this interval. Suppose that is greater than delta. Suppose this length is greater than delta, then I do not know where to go. So now I will change the starting point. What I will ask is, I am choosing a partition P such that length distance between this and this for each x0 xi plus 1, the distance is less than delta. That we can always do. Can we always do that? Think about it. We have done that before also, but do not go back and check this thing for yourself. Can you do that? So once you realize that you can do that, then what happens is that this thing is less than epsilon. Now what? All I need to do is I need to multiply this by xi plus 1, and then so now what is this UP epsilon, UP f minus LPF? That is equal to this difference times the length of the interval. So xi plus 1 minus xi times something here minus xi plus 1 minus xi. Then I am taking the sum over all indices, I is equal to 0 to n minus 1. Now this is common, of course I can take it I can take it out, and each element is less than epsilon. So this whole thing will be less than or equal to, if I take the corresponding sum, this is less than or equal to epsilon times all I am doing is I am just adding the length of all those intervals. How much do I get if I add all these intervals? Yeah, this is I am just taking the partition A to B, I have some intervals and I am just adding these numbers. How much do you think I get? I get B minus A, epsilon times B minus A. So what we have is that if I take a function f, that is see, the main important thing is its uniform condition here. So that we have used, that given epsilon positive, there is a delta positive, so that for any x and y with this distance we have this. So this is what we have used. Okay, suppose you want it to be less than epsilon here, what do? You change this starting point. Instead of asking for it to be less than epsilon, ask that given epsilon positive, there is delta positive, so that for every x comma y less than delta, we have this difference is less than epsilon by B minus A. This is fixed, so you can always do that. So what does this say? This says continuous function is integrable. The same idea with monotone function also. Monotone function may be slightly easier. Let us do that. F from a comma b to r is monotone. Let us check if it is differentiable or not, if it is integrable or not. What I need to do, again I need to give an epsilon positive, I need to fix a partition such that u p f minus L p f is less than epsilon. This is what we are trying to see. We should look for a partition p with this property. Now let us fix any partition p. P is equal to x0, x1 and x2, just this much only. Now x0 is less than x1, x1 is less than equal to x2. What is UPF? That is equal to supremum of f restricted to this times the length of the interval. But as I said, so let us do for an increasing function. I said monotone, so it is increasing or decreasing. So let us do for increasing. If it is increasing, what is supremum? Supremum is just simply x1 times x1 minus x0, right. Then now I should consider f restricted to this interval and take supremum. What is supremum of that? It is increasing, so it is just x2 minus x1. What about LPF? I should take infimum because it is increasing, so the starting point is the point of infimum. So that is equal to there is a small correction here. This is not identity function. So but what I can say is the supremum is f of x1. Sorry, it's f of that. It's not identity. So here also it is the f of x0 times x1 minus x0 plus f of x1 times x2 minus x1. This is not identity function, right? But because it is increasing, the supremum will attain at this element only. So that's what I have written here, fx1, here fx2, fx0, fx1 is the corresponding infimum. Okay. Now what is the UPF minus LPF? UPF minus LPF is equal to, so observe that these two has this as common part and these two has this as common part. So let us take that common. So that is equal to what? Fx1 minus fx0 times x1 minus x0 plus what do we have? Fx2 minus fx1 times x2 minus x1. In general, if I take an arbitrary partition P of length n, what we have is u pf minus L pf is equal to the same thing with more index, summation I is equal to 0 to n minus 1 f of what we have is xi plus 1 minus f of xi times xi plus 1 minus xi. Now we are using the same trick, the previous trick that we used. So one can use the partition P such that this thing has a common bound. So I am choosing a partition P such that this distance is less than epsilon. Epsilon is given, right? Epsilon is given here, here. So I can choose that everything is less than epsilon. So now what I have is less than equal to or strictly less than summation, and there is epsilon at each point. So I can just take it out, epsilon times. What is this? There is a minus here. So at each stage we have the following: f of I put 0 here, that is x1 minus f of x0. Second thing is plus f of x2 minus f of x1. The second step itself, this should get cancelled. Third step, this get cancelled. So what is remaining is after doing all the steps, this is equal to epsilon times f of b, the last element, minus f of a. Again, suppose you want that this to be epsilon, not the next element here. You go to the starting point and change that, choose a partition P such that this length is less than epsilon by this much. So suppose I have this epsilon by fb minus fa, then I have this fb minus fa, and these two gets cancelled, I get epsilon here. So given a partition, given a function p, given an epsilon positive, one can find a partition P such that the UPF minus LPF is less than epsilon. See here we are assuming that FB is not equal to FA, otherwise it's interesting, it's uninteresting. So the same thing one can do for decreasing function also. Here I am doing for increasing function, you can do the same thing for decreasing function. And that's all for this session. In the next session we will do one main result about integration theory, the so called fundamental theorem of calculus. Then we will do some more functions, some more examples, and that's all. So only 3 sessions for integration theory. After that we will start metric spaces, that's all.